Well, folks, we're going to move on in the booklet today. We finished with the conservation of energy. That was the end of page 18. And there are two other concepts that I need to teach you about. One of them is efficiency, and the other one is power. And I think I'm going to start with the power, even though that's a different order than is in the booklet. I think power should have come first. If I had my time back, I would have switched those two things around. So, what is power? Um, Power is a little bit different from work. Power is the rate at which work is done. So, I'm going to start filling this in. So, this is page. I don't know if you have the booklet with you. I hope you do. If you have the booklet with you today, this is page 22. And on page 22 of the booklet, we're looking at power, and power is the rate. I'm going to change that to a bigger font. Power is the rate at which work is done. Like, how fast are you doing work? The faster you can do work, the more power you have. A car that can accelerate from one speed to another speed more quickly has more power. Um, Even though the two cars might do the same amount of work, accelerating from one speed to another speed, the one that can do it faster is more powerful, right? So here's what we say: the power is equal to the work done over time. So if the time is shorter, you're going to do more. You're going to have more power. And the way that this works is 1 watt. That's the unit that we use for power, is watts. 1 watt is 1 joule of work in 1 second. So if you are doing 1 joule of work every single second, that means that you have 1 watt. And therefore, 100 watts would be 100 joules per second. That's what a 100-watt light bulb does. It converts 100 joules into heat and light every single second. A 1500 watt toaster is converting 1500 joules of energy per second into, well, mostly heat if you're dealing with a toaster, or it could be heat and kinetic energy if you're dealing with a hairdryer. But that's what a watt is. A watt is joules per second. So here your work is in joules, your power is in watts. Now this is kind of unfortunate because our work is a W, our power is a P, but we use the letter W for power and J for work. It's just something you have to get used to. So power is the rate at which work. If you know how much work is done and you know how much time it was done in, you know the power. So here I'll do one example with you, and then I'll go back and I'll have a look at the efficiency, and I'll let you get to work. A 55-kilogram child walks up a flight of stairs, moving a vertical displacement of 12 meters in 5 minutes. Well, let's do the first example here. The work done would be mgh. When you're lifting a mass through a gravitational field, the work done is your mg, that's the weight. And then the height here is 12 meters. So the work done would be, I'm going to get the calculator out here now. It's always nice to have a calculator when you're doing physics. Times 12 equals 60, and I'll round this off to two significant digits, so it comes out to be 6,500 joules. That's how much work was done by the person, child in this case, walking up a 12-meter vertical displacement. So that was the work done. And so that was the work done. In each case, it's the same. It doesn't matter how long you take. The time is irrelevant. The time is irrelevant to work because The equation is just mgh. There's nothing in here about time. It's just if you go up 12 meters, it doesn't matter if you take your time or if you run. You will have the same amount of gravitational potential energy, whether you lift quickly or lift slowly. It doesn't make any difference. But the power is different. When we look at power, we're dealing with a different concept altogether. So let's call this the first scenario, the 5 minutes, and 5 minutes, by the way, is 300 seconds. So in the first scenario, the power would be the work done, which is 6,500 joules, all over 300 seconds. Everything has to be in seconds in physics. You can't go using minutes. It won't work. 6,500 divided by 300, and we get 22 watts. So this person had as much power as a 22-watt light bulb running up those stairs. In the second scenario, the exact same amount of work was done. Call this P1, P2. It's the exact same amount of work. It's MGH. But now we're going to divide it by 12, which is 720 seconds, because there's 60 seconds in a minute. So now we got 6,500 divided by 720, and that's going to be 9.0 watts. So work done, the same, power different. Running up a flight of stairs requires a lot more power than just walking up a flight of stairs. Okay, it's this. Oh, no, I did this wrong. It's the question is saying 11 seconds. Oh, for the love of God. Anyway, just let me just do that third scenario. So 11 seconds, P3 6,500 joules divided by 11 seconds. So that is a run up a flight of stairs. Well, you get the picture anyway. If you know the work done, you divide by the time. And this is, oh my goodness, 590 watts. 590 watts, which is kind of like, maybe like a hairdryer on a low setting. But, there's really not much to this power business. If you know the work done and you know the time, you know the power. Okay, so there's nothing more to it than that. And that will allow you to do these questions. Just make sure that everything is in seconds. So obviously this here needs to be turned. So you're going to have to convert to seconds in order to do these questions. And let's see. So force and distance, you can get work from that. Sometimes work is change in gravitational potential energy. Sometimes work is force times distance. Remember, there's 3 different ways that we looked at doing work. Your work is force times distance. Your work can be the change in the gravitational potential energy. The work can be the change in the kinetic energy. 3 different ways that we learn how to calculate work. So sometimes it's force times distance. Sometimes it's something being lifted. Sometimes it's something being accelerated. But all of these can be done here. So let's see, some practice, and the answers are down here. So that will take us down to, now I'm going to backtrack. So that will allow you to do the questions on power on page 22 and 23, and these will not take long. And now let's move back to efficiency, which is on page 19. So here we are on page 19 of the booklet, and we're dealing with efficiency. And, this is kind of like what happens in the real world. In the real world, the energy that you use doesn't all go into doing work. A lot of it is wasted. This is why machines get hot. They get hot because they're inefficient. right? So when energy is transferred from one form to another, useful energy can be lost. And so this would be things like, I mean, if you're looking at kinetic energy, if you're looking at gravitational, if you're looking at, well, there's other ways that you can do work and store it as well. There's other forms of potential. These are all kind of like useful energies. However, much of it may be transferred into, generally, when energy is lost, it turns into heat. That's where all the heat in the world comes from. A car engine, most of its energy is used to just heat up the motor and to heat up the surrounding air. Less than half of it goes into speeding up the car. So cars tend to be pretty inefficient. If you have an incandescent light bulb and you want it to create light, well, sorry, but most of that energy is going to transfer into heat. So it's very inefficient. The LED bulbs are much, much better. They aren't hot. You can put your hands on them. So you get most of the energy turned into heat, but it's still, not 100% efficient. So here we go. For example, an incandescent light bulb rated at 60 watts, which is 60 joules per second, only uses about 3 joules to create light. The other 57 joules is used to create heat, which is not what you wanted. If you want to create heat, you got your baseboard heaters for that. We would say that the incandescent bulb is only 5% efficient because 95% of the energy went into creating heat rather than the light that you wanted. A fluorescent light bulb, on the other hand, uses 12 joules of its energy to create light. And so here, your efficiency would be the useful energy or the work done, right? Like what you actually wanted it to do, divided by the energy, input, like how much energy you actually had to put out to get that work done. So the input energy is usually the the wattage or the power rating of the device. The power rating of the device. So like 1500 watts, a 100-watt light bulb. When you're dealing with watts, you're dealing with power. The useful output is what you get out of it, typically an blank in potential. Well, it would be an increase, wouldn't it? It would be an increase in potential or kinetic energy. So no device is 100% efficient. Input work is always greater than output work. There's no situation where you don't get some heat being generated. It's just one of the fundamental laws of the universe is any kind of transfer of energy from one form to another, any work that gets done, there's always some bleed away. There's always some waste heat generated during that process. So these are the kind of questions you get about efficiency. What is the efficiency of a crane that uses, so here is the input energy. That's how much energy was actually, it's gasoline, the energy in the gasoline that was burned, and it lifts 1,000 kilograms, a distance of 32 meters. So our efficiency is the work done, like what you asked it to do, divided by the input energy. I don't know, maybe I should have called it input energy rather than energy input, but it doesn't matter. The work done in this case is going to be mgh. That's the change in the gravitational potential energy. It's lifted m times g times h. That's your work done. And the energy input is 5.10 times 10 to the 5 joules. Let's bring that down here. So that's going to be 1,000 kilograms, 9.81, 32, which is, fire up the old calculator, times 32 equals, oh my goodness, that's going to be 3.1 times 10 to the 5 joules of work was done by the crane. But it had to burn this much gasoline. So your efficiency is going to equal 3.1 times 10 to the 5 joules. That is our work done. And we're going to divide it by the input energy. 5.1 times 10 to the 5 joules. And the 10 to the 5s here just cancel each other out. You don't need to put them into the calculator. So 3.1 divided by 5.1 is going to be 61%. 0.607, which is 61%. So that crane was 61% efficient. So that's how these questions are done. If you know the work done, and there's various ways that work can be done, right? Force times distance. Remember again that when you're dealing with work, you could be dealing with force times distance. You could be dealing with a change, right? Just recall that your work could be force times distance. The work could be the change in the gravitational potential energy. That's what it was here. The work could be the change in the kinetic energy if you're speeding something up. And then you divide it by how much energy was actually put in, and that gives you your percent efficiency. So then there's a bunch of questions here that you can do, and that will take you down to, oh my goodness, this kind of goes on forever. Well, there you go. Might take a little while to do. But those two concepts can now be, you can apply that knowledge to page, what happened here? Oops. Forgot to hit save or something. So that work is supposed to be, my goodness, force times distance. The work is a delta EG. The work could be the delta EK. And now I got to erase these little thingamajigs down here. There we go. And hit save so they don't drift after that. So you can now do the questions on efficiency. You can do the questions on power. Look, the same thing happened down here. Oh, I can move that up. Deadly. There we go. Hit save and away to go. So that's going to allow you to really get all the way down to page 23. And then after that, we start Hooke's Law, which is looking at springs. So that's your work for today, is to work on the booklet from I've gone through page 19 with you, so 20, 21, and then page 23.